Abhishek, can you hear me? Abhishek Monti, were you present in the last class? Are you there? Okay, I don't know how to take this silence. There are so many possibilities. And as we'll be going to talk about probabilistic reasoning, maybe we can reason out why you are not speaking that well. Anyway, so in the last class, we were discussing the satisfiability solvers, right? And basically we started to take the first step towards it. And we talked about a very simple algorithm, which we call as the DP algorithm, and that stands for Davis-Putnam algorithm. And we talked about three classes of satisfiability solvers as far as the complete satisfiability solvers are concerned. So one was inference based, the second one was the search based, and the third one was to combine this inference and search techniques to design our solvers. So this TP algorithm belongs to this inference category where we were trying to use the resolution rule repeatedly to come up with whether the particular formula is satisfiable or not, right? So there we talked about a method which we call as bucket elimination. The basic idea was that we will be applying P resolution, and P stands for a variable, right? And we want to do this, apply this resolution rules methodologically, and that's why we have classified or clustered the clauses in the knowledge base into buckets, and each of the bucket it is designated for a particular variable. And from top to down, we start to process individual elements or individual variables and try to use resolution rule to come up with new implied or inferred knowledge or clause, and we were trying to add those inferred clauses to the respective or appropriate buckets, right? So I hope the slide is visible. So this was the example that we were working with. So basically, if we try to summarize, so this is the kind of clauses. These are the clauses that are present in our knowledge base. And these are the buckets, individual buckets. And as we know, this DP algorithm has got two inputs. One is the delta. Other one is the ordering of the variable, in which order we'll be processing the variables, right? Sorry. Now, the order in which we have specified the variables, we will create the buckets and try to populate the variables or the buckets based on its appearance in different clauses, right? So for example, this clause, C is appearing here, so that's why this will be going to C bucket, not A bucket, though A is also present here. So here we are respecting the variable ordering that we have started with. And after we have done that, then we'll be applying resolution to individual buckets, and we'll be applying C resolution here, B resolution here, A resolution here, D resolution, and E resolution. Now, if we apply a C resolution here, we can infer a new clause which is not A, not D by using resolution on these two. And we see that this will be pushed to the bucket A. And similarly, we have another, right? And finally, I have nowhere to go, no other rules to apply. And at the same time, we did not encounter any contradiction. So we have our knowledge base to be consistent or satisfiable. But the next question is, I understand my knowledge base is satisfiable, but can you give me the variable or the assignment? So what we are interested in, we are interested in an assignment. So assignment function was phi. So we have to come up with an assignment of the variables, and the variables are A, B, C, D, E. That gives us a satisfaction of the formula of the knowledge base, right? Sorry. So how do we really come up with that assignment? So what we'll do, we will process the variables in the reverse order in which we have presented. So we will take, say, pi prime, which is the reverse of the pi. So it start with E, D, A, B, and C, and start to assign values to variables in the reverse order, right? So, so what we are doing, we are processing the clauses in the forward way, and we are assigning the values in the reverse way. So this is the thing that we are doing, right? Now the rule for variable assignment is, so there are two cases. If you look at the buckets, there are two cases. One is either the particular bucket is empty. Let us say that we are processing, we are trying to assign a value to variable vi. So what may happen? One case is, so the case one is the bucket for vi. So let us name this to be vvi. bvi is empty. And particular case here is D and E. D and E are empty. So what we can do in this case, we can assign any value, right? Now with this, what we can do, let us try to work out the solution as we are going forward. So we can assign, say, true to E. Now the second rule is, if it is not empty, so if BVI not empty, so we'll assign a value to VI in such a way that whatever values we have assigned to the other variables below it. So let's say we are trying to check A, we are trying to assign value to A. Now, while we are doing that, we have assigned values to D and E, right? Now we are trying to assign a value to A. Now, while we are doing that, we see that A is not empty. Now, as A is not empty, we can assign a value by respecting the assignment that we have made for the variables below, right? So we assign a value vi such that together with say I less than j less than n. So let us assume that we have got n variables in our uh, database or knowledge base. So all these assignments of the variables that are below I. So this is our I and these are our j's, right? Now these assignment together should satisfy all clauses in bucket BVI, right? So let us try to follow this, what we are doing. Now D is empty, so we can assign any value. So let us say we assign, say, false here, right? Now what value we should assign to A? So let's say, so we have assigned a value F to D. Now you have to respect the assignment that we have done for D. So we have to place F here. So as we place F here, so this becomes true, right? So this literal becomes true. So this clause will, any case, will be true. It is irrespective of what value we assign to A, right? Now look at this. So if we assign false to D, this becomes false. As this becomes false, in order to make it to be true, I have to assign false to A. So the only assignment that I can make for A is false, given that we have made assignment of T to A, E and F to D, right? Now let us check for B. Now in B, we have chosen F for A. Now as we put F here, so I can put any value to B because it becomes true, right? Now D is false. As we put false here, there is no other way than to assign F to B, right? Now you assigned B and we have to assign C, right? Now how do we assign C? So we have assigned F to be A to be false. So this becomes true in any case. We have assigned D to be false. This becomes true in any case, right? Now we have assigned E to be true. So this will become true in any sort of assignment to C. So I can assign C to either F or T. That does not really matter. So this is how we get the assignment that will satisfy this knowledge base, right? And we can also look at the other kind of assignment which are free to be chosen. So I want you to explore on this, right? So this actually ends the discussion on the DP algorithm. And now let us try to move our focus to model satisfiability as a search problem. So we'll be talking about SAT as search, right? So what is the first thing that will come into mind when we talk about modeling SAT as a search? So what is the problem we have in our hand? The problem is that I have a set of variables, right, in my delta, right? Now, whenever we talk about search problem, there are three things. One is the initial state. The second is the successor function. And the third is what? The goal test. So can you tell me what would be the corresponding choices here? So how do we define a state? So that is the first question. What would be our state? Can any one of you tell me? The SAT problem, what would be our state? Are you all there? Aditya? I don't know what is happening. So if you really don't understand, let me know. So did you understand the problem? Aditi? Hello? No, if I do not get any response, so then in that case, I'll just run the video. So there is no point of just talking. So I'll not proceed on unless I get an answer. So answer may be, well, I do not understand. I'll be happy to explain it further again. Alpon, can you please let me know whether you understand the problem? Did you understand the problem that I'm trying to put forward? Hello?
Yes, sir.
So then can you try to address the question? So in this case, what would be our initial or state description. So what we finally want, if you go back to the earlier slide, what we finally want, we have a set of variable, and finally we want to have what?
Assign.
We want
Yes.
Assign values to different variables.
Right. So we want to assign values to the variables. So if we want to have that, so then let me know what should be our state.
So delta will be our state.
Delta will be our state.
Delta and pi also the ordering.
Ordering, I am not talking about any ordering here. So I'm just happy to see that all my variables are assigned with a value. So try to think of the graph coloring problem. We have n number of states, right? So n number of regions, right? And so then how do you define a state there?
All the regions.
So all the regions are our state. So in our case, what would be our state? If we go by,
Variables.
well, so our state would be all the variables. See, the algorithms, they will be fine, they will be described, but the modeling part is very important. If you don't understand that, then whole of the description of the discussion will be going into vain, right? So the state is basically the set of variables, right? What will be our successor function or init function, init state? What would be our init state? Can anyone else try to answer this?
The first ordering of from which variable we will start the ordering.
uh, if again let us go back to map coloring problem. So there, do we talk about ordering, or I can just pick up any region and color it?
Here we can take any region.
So here we can take any variable, right?
Yes.
So basically our init state will be, we do not have any assignment in on the variables, right? So an empty assignment. What would be a successor function?
explore different values of the variables one by one.
Okay, so we choose one variable, choose a variable and assign a value, right? Or in short, we'd say explore a variable. What will be our goal test?
Assignment of values to all the variables.
Will that be a goal test?
Such that the assignment is satisfiable.
Right. So complete assignment such that delta is satisfied, right? So now you can see that we can model the SAT problem as a search problem, right? So let me try to draw the search tree in our case. So we take a very small example and try to draw a search tree. And then we'll try to make it equivalent to something we have just concluded in the last class, or maybe, yeah, last class. So let's say we have an empty assignment as we have started with, and we pick up the first variable to be A, right? So what are the values that we can assign to them? Either true or false, right? Now, as we can assign a value t to a, let us explore other variable. It can either be true or it can be false, right? Explore another variable. Say, let's say t here. Let us say that we do not have any other variable. Now we have got w1. And if we have, say, if we have got w2, and maybe here we can explore c again to get, say, w3 and w4. So we can keep on going like this until we will be having something like, say, w8, right? So look at each of these leaves, right? So each leaf, what does it really signify? It is a complete assignment, right? And for each leaf, we will test for satisfiability. And what will that concern? It will just try to check or search for the leaf that satisfies a delta, right? So now can you think of some problem that we did earlier and that is kind of similar to what we are uh, discussing now? Any idea? This is very similar to a problem that we have discussed maybe a few days back. So here the solution will, yes. You're
Depth
saying something.
first.
Can you repeat, please?
Depth first search.
Depth first search. Depth first search is a search technique, but my question is, so here I'm well, okay, DFS will come later, of course. This is a good, I'll say, good response. But what I'm trying to see, do you see these class of problem to be equivalent to a class of problem that we have discussed earlier? Let me name it. So can you see a similarity of this kind of approach to, or this kind of problem with the category what we call as constraint satisfaction problem? So in constraint satisfaction problem, what we had in contrast to general search problem, the solution will always lie at the lowest level or the deepest level in the search tree, right? So do you see the similarity between the CSV problem and this problem? So
Yes.
in general search problem, the goal can be anywhere in between. But in CSP, you are guaranteed to have your search problem at the greatest depth or deepest level of the search tree or search graph, right? And as you mentioned that we have used DFS to solve this kind of problem, right? And here again, whatever we will be doing, we'll be using DFS, nothing but DFS, but in a different way, of course, right? So let me first write down a kind of degraded version of DPLL, which is entirely based on DFS, and we'll try to improvise that to make it more efficient. So we'll be talking about a different type of algorithm, which we call as DPLL algorithm. Uh, and so let me write down the names: Davis, Putnam, then you have Logman, and finally you have got Loveland. So we'll be discussing an algorithm first, which is DPLL minus. So you'll be not be using all the features of DPLL, right? So we start with something which we need to have, that is the delta. And the other parameter that we have to have as we are doing DFS is the depth, right? And what will it return? It will return SAT, satisfiable, and if it is satisfiable, then it will return the variable instantiations. Or it may return unset, right? So basically it will be a recursive algorithm, and there are two steps that we need to really define. One is the base step. So what would be our base step? The base step is of two types. Now if you see that our delta is empty, we do not have any other clause to consider. So that is the case of satisfaction, right? So there we will be returning just one empty assignment because I do not have anything to assign. I do not have any variable, any clause. We do not have any clause, so that means we do not have any variable to assign. So you just return an empty assignment, right? Else, if we see that we have a phi in our delta. So these are the two cases we have discussed earlier. So one case is we have something like this, which is the case of unsatisfiable. This is a case of unsat, and maybe in some cases we will arrive at a situation that we do not have any contradiction and we do not have any clause to explore. So that is the case of SAT. So this is the case of SAT, and this is the case of unsat. And if we have this kind of situation, we'll be returning unsat, right? Now we'll be going into the recursive step, right? So in the recursive step, what we will be doing? So let us go back to the earlier slide. So what we are doing? We are taking a variable and we are assigning in one branch the truth value to be true. In the other branch, we are assigning a truth value to be false, right? And we are keeping on doing this until we get a satisfaction, right? Now, there may be two cases that will be happening. Either in this branch we get SAT or unsat. Now, if we get SAT here, what we will be returning? We'll be returning a variable instantiation for the remaining variables. So we have already chosen A to be true. I have to choose B and C instantiation, right? And if we get an unsat, then what we'll be doing? We will be exploring the other branch. So that is how we'll be devising our algorithm. And this is going with the philosophy of depth first search, right? So in the first phase, if we look at the left branch, so what we'll be doing? We'll be conditioning our knowledge base, the existing knowledge base, with a variable, the positive choice of the variable P in the next depth, and we'll send that we are doing it for depth P plus 1. And if we see that this is not equal to unsat, then what we will return? So what if it is unsat, what will it return? It will return a set of variable instantiation for which the remaining portion, basically this portion, is satisfiable, right? So in that case, what we'll be doing? We'll be saying return L union P D plus 1, because we know that this choice has led us to satisfaction, right? And what is the other case? The other case is we are calling this recursive function on the other branch, which is the negative branch. So for one literal, we are taking a true value in one left branch and a false value in the right branch, right? So if we are choosing this branch, we have to condition this knowledge base on P negated PD plus 1. And of course, we are doing this for the depth T plus 1. And if it is unsat, not unsat, then we will return L union negated P D plus 1. And how do we call this? And if we do not have anything of this, we say unset. Right. So what will be our first call? So our first call would be DPLL minus. We will be starting with the original knowledge base. And what is the depth we'll be starting with? We'll be starting with depth 0. So let me try to do a very small dry run of this algorithm on the example that we have given earlier, right? So our knowledge base is not empty. So this is not satisfied. So this if will not be entered. This will also not be entered, right? And then we'll be making a call in the next level. And in the next level, we are choosing, say, A, right? So we'll be conditioning delta over A, right? And we'll be setting D to be 1. So our next call will be DPLL minus delta condition over A and depth 1. And in this part, if we see that this path is not satisfiable, then we'll be going to this path, right? And in this part, what will be our call? Our call will be DPLL minus delta negated A. So we are taking this path then, right? And of course, the same depth level, right? And if we get a satisfaction here, what we will do, we will explore the remaining path or solve the remaining path using a recursive call. And we have got this B and C. We'll try to see what are the instances of B and C that gives us this satisfaction, and we'll add that. So that will be coming into our L. So let's say for the sake of example, for say B equal to true and C equal to say false, we have got a satisfaction of delta A, right? So in that case, what we will have in our L will contain B equal to T and C equal to F, right? And we have already set A equal to true. So what would be our final assignment? Our final assignment will be A equal to true, B equal to true, and C equal to F, right? And this is a very simple algorithm which you can explore using any example, right? So let us try to do a kind of example and try to see whether we have understood the idea or not, right? So the example that we'll be doing is delta negation A, B, negation B, C. So this is our delta. So let's say we have started with A, right? So the first branch that we'll be following is T. So it will be assigning to value T to A, right? So that means what we are doing, we are conditioning delta over A. Now, if we condition delta over A, what would be the state of our knowledge base? The state of our knowledge base would be, so this will become false, and B I don't know, and this again I don't know what would it be. Now in the next phase, what we'll be doing, we'll be trying to assign a value to B. And as we are doing DFS, we'll be assigning a value T here. And what we are doing here really, we are conditioning delta over A and B. Now, if you condition this delta over A and B, so what will happen? So we'll have F here and we are assigning T here for B, right? And what will happen to this? So this will become false and C will remain as it is, right? Now we'll check for C. First, we'll assign a truth value to be T. So delta A, B, C. So what we'll have as output F, T, and this will F and T. So basically in this path, we are getting a satisfaction. Now instead, say we have chosen say A, B and not of C. What would have happened? So basically we'll be starting from here. So this F and T, and here we'll be getting all false, right? So we'll be having a empty clause, which is contradiction. And finally, we'll be having a contradiction here, right? So we have something W1 here, which is fine, satisfiable. If we assign F here, we get W2, which is not satisfiable, right? Now, if we try to do the other branch, which is F, so what we have delta A negated B. So what we'll have here in the first place, this is false. So this becomes false. And irrespective of what we have here, we get a contradiction. And here you can see that we do not really need to explore C further. So I do not really care what would be my value for C. I get a failure here, right? And likewise, you can check that we can assign a value F to A, and then we can expand it further, T and F. And I guess for C, we have this path to be satisfied and this path to be not satisfied. And here we'll be seeing that I do not really need to assign value to C, any value to C. Here we'll be getting a success. So what is the kind of point that I'm trying to make here? That DPLL minus, it may detect failure early. So if we would have taken a very naive DFS, we had to reach this leaf node and then we need to check whether it is success or failure. But DPLL does bit better and it can prune some part of the search tree, either to detect failure early or either to detect success early, right? So now let us try to see what is the kind of amount of work that is done by this DPLL minus, right? So we are trying to see the amount of work done by DPLL minus. So basically, how can we get this? We can get this just by seeing how many nodes in the search tree that is being explored. If we do that before we get a satisfaction. So what is our goal? Our goal is to find an assignment for which the knowledge base is satisfiable. So what we'll be doing? We'll be keep on expanding or assigning the values to the variables until we get a satisfaction. At the point we get a satisfaction, we stop there and we'll check how many nodes in the search tree we have explored. And that will be giving us the amount of work that is done by DPLL minus, right? And that gives us the notion of something called termination tree. So what is termination tree? Termination tree is exactly the subset of the search nodes of the search tree that is actually explored during our search, right? Well, to explain this, let me take another example. So let us take delta to be A, B, not B, not C, C, not D. So you start with A. So what we are doing here, we are conditioning delta over A, right? And if we condition over, so here we do not do any conditioning. We have delta here, right? Now, as we follow the path A equal to true, then you are doing conditioning over delta A, right? And as an outcome of what we are getting something like, say, B, because if we set delta to be true, this is becoming irrelevant. So we have B, then BC will be there, not B, not C will be there, and C, not D will be there, right? So this is my status. Now we'll be exploring or expanding B. Now, as we expand B, we try to do a conditioning that is delta AB, right? Now, as we do delta AB, what is the output we'll be getting? So you can really tell. So this will be gone, and this will be converted to only not of C, and this will be remaining the same, right? So we have not of C. So let me write it. So we have not of C and C not of D. Then let us try to expand, explore C, right? Now, if we assign the truth value to be true, so that means we are doing a conditioning on A, B, and C. So what happens? We get a contradiction, right? So we get a contradiction at this point. Now, what we'll be doing? We'll be expanding the other path, which is delta A, B, negative C, right? So if we do that, what we are getting really, we'll be getting, so this will be gone, and only thing that will be remaining is not of D, right? So we have not of D, right? Now we have only variable that is remaining is D. So if we say D here, so we are conditioning delta over AB not of CD, we get a contradiction here. So we get a contradiction here. And we just set it to be false. So we have this A, B not of C, not of D, we get a satisfaction. So this is the kind of amount of work that is being done by the DPLL minus algorithm, and this is basically called the termination tree, right? Now, one thing that you can see that while we are doing all this, we are also maintaining the assignment. And finally, what is the assignment that we are getting? We are getting A equal to true, B equal to true, C equal to false, and D equals to false. So this is the kind of assignment that makes this particular knowledge base satisfiable, right? Now, with this, let me take you to another observation. So let me first write down the state of exploration. So you are conditioning delta over A. What we had earlier, we had B, we had not B, not C, then we had C, not D. So at this point, what was our base condition? Our base condition is either delta is equal to phi or phi belongs to delta. So this is the case of SAT. And this is the case of onset. Do we see anything happening here? Do we see any of these cases happening here? Can anybody tell? This should be very straightforward. At this point, I have just done a conditioning over A. So that means I have just set A equal to true. As a result, I have got an updated state of the knowledge base. So that is what we have. We have just need to look at this and tell whether either of these condition is getting satisfied or not.
No.
That should be quick. Hello?
No, sir. No, sir.
So no, so we are not get any such cases. So at this point, DPLL minus cannot decide success or failure. Right? But we see that as we are doing this, these kind of conditioning stepwise, then followed by this, we did something like say delta A, B, not C, and then finally we did something like delta A, B, not of C, not of D. And at every point, what we are performing, we are performing resolution, but what kind of resolution we are performing here at this point? So we have the delta and we are setting A equal to true. What does that mean? That means we are adding A, this clause to the knowledge base. We are adding to the knowledge base. So are you agree? Do you agree with this? Hello?
Yes.
Okay, so, and as we are doing this, then the next step that we are performing is our resolution. And what is the resolution we have done? So our original was not of AB, right? So we resolved it with not of AB. So this is a very important idea. So that's why I will spend some time here. We are performing one unit resolution here, right? And we get something like B. And our knowledge state of the knowledge base is this now, right? Now at this point, we are conditioning this over B. So what does that mean? We are adding this clause with the current knowledge base, current conditioned knowledge base, right? Now, as we do that, after that, what we are doing? We are again performing an unit resolution with this to get negative C. What we are doing here? We are setting this negative C to be true, negative C to be true, right? So we are on top of this. So this is the state of knowledge base now. We are adding another clause and we are performing another unit resolution. And here on top of A, B, not C, we are adding another unit clause and we are performing resolution. At every stage, what we are doing, we are adding one unit clause, adding unit clause. And what does that facilitate? That facilitates applying unit resolution. Now that brings us to the idea that what if we can apply this in unit resolution as far as we can. We start with A and we just try to see the opportunity to apply unit resolution, right? Repeatedly. as far as we can. Now, if that can be done, our knowledge base will be reduced to a very small set. So let us try to illustrate the idea that I'm talking about. So we have, after conditioning over A, we have this. Now, if we condition this, again, we have a case for applying unit resolution. So if we apply unit resolution, what we'll be getting? We'll be getting negative C and C not D. Now we can apply unit resolution here over C. And if we apply unit resolution over this, we just get D. And at a single step, we are coming from this stage to this stage. My knowledge base is getting reduced to a single decision, which we can perform very easily. And this kind of propagation of unit resolution or repeated application of unit resolution in a chain is what we call as unit propagation. So what we are doing basically, the basic idea is we are propagating the unit resolution in a chain as far as we can. And what is the motivation? The motivation is that there I do not need to take any decision. And what is the benefit of that if we do not take any decision? Can anybody tell me? I want you to realize this part. So this is very interesting. So what I'm saying, I can readily apply unit resolution here, right? And that means as I can apply unit resolution, I do not really need to worry about what will be the value of B. I have just set B to be true because I need to make this to be true. I do not have any decision choice, right? I am bound to set B to be true. I cannot set B to be false, right? So that what does that imply in the if you think in terms of the termination tree or the search tree? Will anybody try to give it a thought?
That forcefully directs us towards a solution.
So forcefully, we are forcefully going to, maybe we are not, maybe we can go to the solution or it may not be, but what we are doing, so when we are taking a decision, say let's say A, I have a decision point T and F. If I get a failure here, I can explain this path, right? But contrary to this, if I say that I cannot have a choice than A equal to true. So if I get a solution, I will get a solution here. If I do not get a solution, I do not get a solution. So I do not need to expand this part further. So that is the kind of benefit that we are getting. And that we are getting using this unit propagation, right? So can you give me a couple of minutes to wrap up this idea? Hope that will be fine. I just need 2 or 3 minutes. Okay. So the first thing that we'll be doing will be closing the delta under CNF. Sorry, under unit resolution. So what do you mean by that? So this means that we are applying unit resolution as far as we can. And after that, whatever is remaining with delta, that is, we are saying that we are closing delta with this unit resolution. And in this process, we will be collecting all the unit clauses. And what is the motivation? Because these unit clauses, they have to make true. I do not have any other choice, right? And then finally, whatever we are remaining with, we'll be performing this check for success or failure. So we define two things. One is I. I is basically a set of literals that are either present as unit clauses, either present as unit clauses in delta, or were derived from delta using unit resolution, which we just did, right? And we define something called gamma, which is the new delta. So basically this is delta conditioned over I. So whatever, so this I will be collecting all the variables or literals that are appearing as unit clause, and we will be conditioning this delta over this I, right? So let us take a quick example. So let's say we have this A, not of A, not of B, B, C, then we have not of C, D, and say not of A. So what will we have in our I? Of course, this will be there, right? And apart from that, we can apply resolution on these two to get not of B. So not of B will be coming into our I. Now, as we have not of B, we can perform an unit resolution with that, and that will give us C. So C will be being collected here. Now, as we have C, we can resolve this with not of C to get D. Now, as we do this, so what will be our gamma? Can anybody tell? Gamma is basically delta conditioned over I. So what that would be? Can anyone tell? I promise this is the last thing that we are doing today. I'm conditioning delta over I. So what will happen? I means
That is a goal.
that is a satisfaction, right? So you get a SAT here.
Yes.
So you see, we are really improved our search technique, and in the next class I start talking about the algorithm that will be built on top of that, and that is really very trivial. We just first do this unit resolution or unit propagation, and then whatever remaining with us, we perform DPLN minus as we have done earlier. So well, so I'm done for today. In the next class, I'll be trying to complete the SAT module, and in the next class, we'll be having a demo of a tool that makes use of all these algorithms. So I'm done. Thank you. So if there are any questions. Okay, if there are none, so let us close this class today. Thank you.